This is the last chapter of the semester in Chem 203. So we're gonna look at acids and bases and salts. And by the way, salts in this context is a chemical term. It's not what we normally think of as salt or table salt. So it's just a teaser. Definitions will come later. All right, so let's get started. Get all my utensils together. All right. So there are lots of topics that we're going to cover today, and I hope we have enough time to get through all of them, because each one is important in its own way. First of all, what's an acid? What's a base? We introduced the concept of acids in the chapter on nomenclature, where we actually had to learn how to name acids, right? So you remember that we classified an acid as a compound that started with an H, at least one, sometimes two, sometimes three, and then something else. And we learned how to name that compound. If it had an oxygen in it, then we did not start the name with hydro. If there were no oxygens, we started the name with hydro. For instance, chloride becomes ic, chloric, hydrochloric. Since there's no oxygen, hydrochloric acid. This one, NO3 is the nitrate ion. Eights become ics in this context, and there's no hydro. So it's just nitric acid. Okay, so we're going to carry that concept a little further into the chemical world. How are acids defined by chemists, and what types of reactions in which they occur? Okay, the first coherent theory concerning acids was proposed by Svante Arrhenius, a Swedish chemist, in the latter part of the 19th century. What Arrhenius said was, and what he had noticed in his work with proteins, he was what we'd call today a protein chemist, was that acids always had a hydrogen in their makeup, so that when they reacted, when you put them in aqueous solution, you would get a separation here of those two parts of the molecule, right? This A could be anything. Well, not anything, but it could be a lot of different things. So that was his definition of an acid. His definition of the base was similar in that we had some part of a molecule, and then attached to it was a hydroxyl. Remember, the hydroxyl is a polyatomic ion, OH minus. And when we put it in aqueous solution, then it would dissociate into this cation plus the hydroxyl. And that works for 99% of the acids and bases that we put into aqueous solution. Now, there's a difference in the chemistry that happens. For acids, they go through a process of ionization in which the molecule itself is stable in this form, and it doesn't exist like an ionic compound, like that. That's not the way it is. It's more closely akin to a covalent bond. So when an acid goes into solution, it must ionize. Electrons must be transferred. So we transfer an electron from here to here, And that makes this positive ion and makes that a negative ion. That's ionization. Okay. For bases, for Arrhenius type bases, where you have some part of a molecule and the hydroxyl, these do exist as positive and negatives. They are ionic compounds. So when you put them in solution, all they have to do is dissociate. So this is a process of dissociation. Okay. It's a fine distinction, but the focus for acids is on the molecular, and the focus for bases is on the ionic, for the Arrhenius definition of an acid and a base. All right, so this is your artist's idea of of a ionization on the left versus a dissociation on the right for the base. And that's straight out of your book, so you can ponder that one as long as you want on your own time. So which of the following describes an Arrhenius acid or a base? An acid is a substance that produces hydrogen ions in aqueous solution, and a base is one that produces hydroxides ions in aqueous solution. And the hydroxides must be part of the structure, part of the formula. All right. Like I said, that covers over 90% of the acids and bases that we encounter in chemistry. But there are a few that don't behave. Now, the acids, that's fine. They're okay. But the bases can produce hydroxyls without a hydroxyl being present in the molecule. And the perfect example of that is ammonia. When we put ammonia in solution, it produces hydroxyls, right? So how does that happen? Well, we need a new definition. What we discovered was water, the water molecule, is an active player in acid-base chemistry. So when we include water here, then what we get is instead a transfer of a proton. Now, I'm going to use the word proton for hydrogen ions. That is a hydrogen ion. And for most hydrogen atoms, this would be a proton, right? A proton surrounded by one electron. So if you remove the electron, you got a proton. Now, that doesn't include isomers, right? Sometimes you can have a neutron here, or you can have two neutrons, right, for deuterium or tritium. But for my purposes, I move back and forth freely between hydrogen ion and proton. Because if we say hydrogen ion, it could be this, or it could be this, right? You can make an anion out of a hydrogen atom. So a proton, using the term proton, guarantees a positive charge. All right. So how do we deal with this? Well, we're going to transfer a proton from this water to that molecule, right? So this is no longer a dissociation to make a base. This is actually an ionization to make a base, because these are both covalent compounds, right? And what you end up with is a polyatomic ion, ammonium, and what's left over from water? Well, remember the structure of water? It's like this. If we take that one away and leave the negative behind, then what we get is a hydroxyl. And that positive proton then, it transfers its positive charge to this species right here. So that accounts for the basic characteristic of ammonia dissolved in water. But we can't use the Arrhenius definition anymore because that base doesn't have a hydroxyl. So in 1923, two scientists independently proposed a solution to the problem. There was Johannes Bronsted from Denmark and Thomas Lowry from England proposed another way of looking at acids and bases. And this is actually the chemistry that happens. When you look at it this way, for ionization, that implies that the hydrogen ion is independently floating around in the water. And they do not do that. We never find independent hydrogen ions floating in water. They're always attached to something. So protons are transferred. And that's the concept that Bronsted and Lowry were using. All right? So, let's give some space for Bronsted and Lowry. All right. Okay, so what they said was, we're going to focus on proton transfer only. The one that donates a proton is the acid. So anything that can donate a proton, like that, is an acid. Well, if it donates it, it has to go somewhere. So in this case, when you put it in solution, it donates a proton to water and produces the hydronium ion, polyatomic ion. Okay, what's left over is the anion from this transfer. So this proton is transferred to that one. That makes this an acid. And by Bronsted and Lowry's definition, the proton acceptor is the base. So that makes water the base because it accepts the proton. Okay? All right. That covers almost all of the rest of the acids and bases that we encounter. The concept that I don't think we're going to mention in this class is used to deal with acid-base type reactions in non-aqueous environments. Right? So we don't have to deal with it because we're staying in the aqueous realm right now. Okay, so acid-base. And there's your definition. Acid donates a proton, a base accepts a proton. There's another one, HF, hydrofluoric acid. All right, so if we did that one, and these are all in aqueous solution, well, except for water, right? Water is a pure liquid, right? And we get the hydronium plus what's left over. Like that. Okay. This obviously is acid because it donates the proton. Water becomes the base. By the way, water can function as either an acid or a base. It depends on the environment. In this case, it's functioning as a base. It's a proton acceptor. But when we do that, we create products. This one now can donate that proton to something else, or even back to, it can donate that proton back to the fluoride ion and make HF. That's why we have the double arrow here, because the reaction can go forwards or backwards. So the acid produces a base, a proton acceptor. This is the proton donor. It produces a proton acceptor. And to keep our terminology from getting all confused, we call this, rather than just say acid base, we say this is the conjugate base of that acid. All right? And that makes this one a base, and this one is the conjugate acid of that base. All right. Conjugate acid-base pair. What do we mean by that? Well, if we look at the reaction, you see what's happened here. Let's take this acid and this conjugate base. What's the difference? And what are the similarities? The similarities actually are this part of the molecule, F, is still there, right here. Right? What's missing? What's missing is one proton. These acid-base reactions, we consider them from a chemical standpoint as one proton transfer at a time. So if we had something like this, sulfuric acid, it would undergo a reaction that would transfer the proton to water, make the hydronium, and what would be left behind? HSO4 minus. Right? We only transferred one proton at a time. So that's the condition. You have to have the same thing here and here, plus only one proton at a time. Right? Now you can still take this one and undergo a second reaction with water, but that sets up a different acid-base pair. This acid-base pair, acid conjugate base pair, is HF F minus. And that should be highlighted right there. Okay? Now you can say the same thing about water. This would be the base, this would be the conjugate acid. So the acid-base pair would be hydronium ion, water molecule. Or the acid-base pair for this one would be sulfuric acid, hydrogen sulfate ion. Okay. Now, I mentioned earlier that water can act as an acid or a base. This is called, it has several names. We could call it amphiprotic, which means both protons. Amphi or ampho means both. Or amphoteric means both directions. And water's not the only molecule that will do this. Right? Let me make some room here. Oops. Okay, water will do it, and ammonia is another good example. How does water do it? Let's look at it that way. Pure water. Let's say you have a container of pure water, nothing else in it but water. It will do this. Right? It will transfer a proton. Now, which one did it? Which one lost one proton? Which one gained one proton? We don't know. We just arbitrarily say this is the acid. This is the base. So if we transfer a proton from here to here, that makes a conjugate acid here. And this makes a conjugate base for that acid. And this acid has a conjugate base here. This is the amphoteric nature of water. All right. Oh, I mentioned ammonia. Ammonia can do this too. If you have what we call anhydrous ammonia. That is, there's no water. It's 100% ammonia. And believe it or not, farmers use anhydrous ammonia to fertilize their crop with nitrogen. They have to have special equipment. They have their tractor. Behind their tractor, they pull this huge stainless steel tank. And then all the pumps and all the sprayers, no, actually not sprayers, injectors. Injectors must be stainless steel. Otherwise, they'll be corroded with this. And since anhydrous ammonia will instantly vaporize once it's released from the tank, then they have to use stainless steel knives, injectors that cut down into the soil, and they put the nitrogen, the ammonia, down into the soil where there's moisture, and it instantly reacts with water, and that fixes it there. Okay. And if you just try to spray it on your field, you'd blow it out your sprayers and you'd have ammonia all over the place, choking people to death. But inside that tank, we've got anhydrous ammonia, and it can react like this, transfer a hydrogen to this one, right, just like that. And I can't write aqueous here because there's no water. So I'm not sure what the subscript would be, or the parentheses. And then what's left? Well, NH2, but left a negative behind. So this is the ammonium polyatomic ion, and this is the amine polyatomic ion. So ammonia can be amphoteric too. All right. So if an acid only has one proton that it can deliver into solution, transferred to water, for instance, then it's called monoprotic. And there are several of those. We studied those. Hydrochloric, hydrofluoric, hydrobromic for that matter. Okay. Nitric. Okay. You can have nitrous also. Remember that one? Right. Those are all monoprotic acids. Diprotics have two available protons for transfer. And I just showed you one of them, sulfuric, right? Or we could have sulfurous, like that, right? That's a good example. And if you have three, that's a triprotic acid. Best example of that is phosphoric acid. There. Okay. Or phosphorus. Right. They're both triprotic acids. They have three protons available. But like I said earlier, when they react, when you put them in solution, the reactions occur one proton at a time. And those that are diprotic or more are lumped together as polyprotic. There might be some with 4 hydrogens. Probably are. I just can't think of any mineral acids like these. There are lots of organic acids that have 4, 5, 6, 7, 8 protons available. Okay. Now we want to expand our definition for acids in chemical terms. What do we mean by a strong acid? The popular concept of strong acid is anything that will burn you if you touch it. But in chemical terms, that's not the concept we're looking for. That's referring to corrosivity. We'll talk about that again later. In chemical terms, strong acid means virtually 100% of the acid is ionized. Well, let's use a real example. Let's use hydrochloric acid. There we go. Aqueous water transfers a proton and leaves behind the anion. There we go. This is a strong acid. In fact, it would probably be more accurate to just write a single barbed arrow, because it's going to go all the way to the right and not come back. Essentially, if there's anything left over here, it's infinitesimally small concentration. Here's some examples, right? Hydrochloric, hydrobromic, hydroiodic, those are all halogens, acids of halogens. Now, why don't we have HF up there? Are we saying that HF is not a strong acid? Yeah, that's what we're saying. HF is not a strong acid. It does not completely dissociate in aqueous solution. Whereas hydrochloric, hydrobromic, hydroiodic, they all do completely dissociate. Hydrofluoric is, we're going to define it in a minute, is a weak acid. It only partially dissociates. I should not use that word. It only partially ionizes. Nitric acid is strong. Chloric acid is strong. Perchloric acid is strong. Sulfuric acid is strong. Sulfuric acid would undergo this type of reaction. Hydronium ion, and what's left over, right? That is the strong acid reaction for sulfuric. Only the first proton. Okay? This one right here could then undergo a reaction with another water molecule, and it would produce the sulfate polyatomic ion plus another hydronium. Right? These are all aqueous, 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 aqueous. The point here is that sulfuric is a strong acid for the first proton, but it's a weak acid for the second proton. Think about it. This is a negatively charged item. And in order for it to ionize further, you would have to separate this positive charge from that negative. Okay? And it's much more difficult to do, purely based on Coulombic attraction. Opposites attract, right? That hydrogen wants to stay with that negatively charged sulfate. Okay. But that is considered a strong acid. All right. Weak acids, on the other hand, only partly dissociate in aqueous solution, which means that we can establish an equilibrium in this reaction. Now, I can't recall if we discussed equilibrium in detail, but I'll try to make sense of it now. When we have, let's use HF. Since I said it was a weak acid, let's use HF. Okay, in aqueous solution plus water, that just means the reaction can go forwards or backwards. And then we have the hydronium ion plus the fluoride ion in solution. Now, what happens during this process? The forward reaction produces these products. And then once you get enough of these products built up on this side, then they can start interacting again. And this can be an acid-base reaction and go back the other direction. When we observe the concentrations of each of these, of course, we can't observe water's concentration because it's too high. It doesn't change. But this will change, that will change, that will change. And when we observe, and measure their concentrations, they're stable. They don't change. Measure those concentrations. Once this reaction has reached equilibrium, you don't see any further concentration changes in these species. Okay? That's what we see. That's what we observe and measure. But what's going on in the microscopic world? The rate of this reaction and the rate of the reverse reaction are exactly equal. You still get this forward reaction, even though we think it's stable, it's static. It's not static, it's dynamic. This rate forward and this rate backwards are occurring at a furious pace, but they're occurring at exactly the same rate. That's equilibrium. Okay, so that being said, for weak acids, the equilibrium position, measured concentrations, put this side to be higher, the dominant side, because that acid does not ionize very much, just a little bit. So this is very low concentration. This is whatever concentration you put in that solution, right? So the left side dominates. Strong acids, the picture on the left shows you a strong acid where virtually everything from HA goes to the far right side. Whereas with the weak acid, you get this HA reacting with water, and most of it is still unionized acid. But you do get a little bit of the hydronium and the anion, the conjugate base. Okay, that's the chemical difference between strong acids and weak acids. Okay, strong bases. These are all, these could all be classified as Arrhenius bases because they each have a hydroxyl in their makeup. Right? Notice lithium, sodium, potassium, rubidium, cesium, those are all group 1, all alkali metal sources for the cation. And then you just add a hydroxyl. And since the group 1s are always +1 charge, you can only have 1 hydroxyl for each one. Group 2s, calcium, strontium, barium, those are all considered strong bases, right? And the reason these are all considered strong bases is we assume that they're in solution before we see the dissociation. So let's say potassium in aqueous solution. It dissociates into that completely, goes into solution completely, producing these. None of that is left. Okay? When we think of that in terms of what was it before? What does potassium hydroxide look like if it's not in solution? Well, sometimes it comes in flakes, sometimes in little granules, sometimes in little pellets, right? So it's a solid. And when we put it in solution like this, then it undergoes that reaction and dissociates, right? And when it dissociates, it goes completely to the right. Now, the reason I'm emphasizing that point is because I want to move to the group 2 hydroxides, calcium hydroxide, for instance. It will produce a calcium ion and 2 hydroxyls. All right. Now, here's the rub. Calcium is only partially soluble. Calcium hydroxide is only partially soluble. So, when we say strong base, we mean that whatever part of the calcium hydroxide actually goes into solution completely dissociates. But there's a lot of it left undissolved that does not go into solution. So, in chemical terms, it is a strong base because whatever makes it into solution dissociates. But it's only partially soluble. I know that's a fine distinction, but it's an important one when you start doing reactions with these compounds. Okay, which of the following would be the correct representation of a strong acid when placed in water? Right, the one with the big arrow to the right. That one. In fact, the little arrow should be even smaller. All right. Now, we talked about equilibrium. Let's go back to that concept. Equilibrium of an acid in solution. Let's say we have a weak acid. Let's say a weak acid like HF. Okay. And it reacts with water. Water is the base. And it sets up an equilibrium with the hydronium and the fluoride ion. Okay? Now, what we've discovered is not just for acids, but for all chemical reactions, you can have an equilibrium set up, reaction going to the right versus returning. Right? You get an equilibrium established. And we can write an expression, a mathematical expression, in terms of the molar concentrations of each of the components. In this case, we're going to use molar concentrations of HF, hydronium, and fluoride. We don't use water because it's a pure liquid, and pure liquids do not change concentration. So we don't include them in the expression. So the expression here, that acid ionization constant, is the molar concentration of hydronium times the molar concentration of fluoride. Notice products in the numerator. And in the denominator, we have the molar concentration of HF that remains after equilibrium is established. These square brackets mean two things: equilibrium concentrations, and the concentrations are in molarity, moles per liter. Okay? Now, in some of these expressions, you can have, not in acid dissociation, because we only do one proton at a time. Right? So the coefficients are always one. Right? So the power, if we had a power here and here and here, it's always one. But for other types of chemical reactions where you can write a K expression, an equilibrium constant, you can have powers. For instance, this is a generic. If we have this reaction, reactants, we produce products like that, we can write an equilibrium expression for this one as long as these are all in solution or gases. Right? If they're solids or pure liquids, we don't include them. Right? So we're going to assume this one, C, to the little c power times D to the little d power divided by A to the little a power and B to the little b power. That will be for any chemical reaction. This is specific for acids, but it's based upon that equilibrium. This is called the law of mass action. Okay. Now, that's how you determine the equilibrium constant for acid ionization of a weak acid. We don't use it for strong acids because what would happen? With a strong acid, everything would be over here, right? So you'd have values here, but what would that value be? It would be 0. Anything divided by 0 is infinity, right? So the acid dissociation constant for strong acids is infinity. Okay, there's another way of expressing this ionization in terms of percent acid ionization. And all we need to do there is to know what is the concentration of this species divided by the concentration of that species times 100, right? Molarity here divided by molarity here times 100 cancels out the molarity, and we get a percent value, acid dissociation. Now, this value varies with the concentration of the acid, right? And that is referencing equilibrium position. It will still be in equilibrium, right? But if you use a different concentration, then this side will be a different concentration, and that side will be a different one, and you get a different percent dissociation calculation. But if you calculate the Ka with all of these terms included, this one is always the same for a fixed temperature. This is at some temperature. Right? If the temperature changes, then the constant changes. All right. These terms are related. If we try to relate the concept of acid strength, right? We said there are strong acids and there are weak acids. Well, the strong acids are virtually 100% ionized, but the weak acids have a range, right? Some are very, very weak and some are not so weak. So if we express their strength, acid strength in terms of dissociation, then the percent ionization would tell us that the higher the percent ionization, the stronger the acid. I mean, they're directly proportional. Also, if the Ka increases, we have a stronger acid. Even though it's weak, it's stronger than some others. Why? Because this term is in the numerator. If this gets bigger and that gets smaller, then Ka has to increase, right? It's just a mathematical law. Quotients are like that. That one decreases, this one increases. It's got to get bigger. So that speaks to increasing acid strength as well. Okay. Also, as the Ka increases, the percent acid dissociation calculation also increases. So these are all terms that are directly proportional to one another. Now, the base ionization constant, I guess that could be valid in, we usually consider it dissociation, right, for the base. But, oh, and there's something missing here. Look. Well, maybe not. The base could be charged or it could not be charged. That's possible. So here we're saying that it's not charged. And that's okay. So the equilibrium constant for the base we have a Ka for the acid, we can write a Ka for a base also. Let's see, let's make room here. So whatever the base happens to be, doesn't matter. Let's say it's well, if this is the acid and this is the conjugate base, let's use this right here, that fluoride. What if we put fluoride in aqueous solution without the hydrogen already attached? Can you do that? Yeah, sure. Potassium fluoride or sodium fluoride, they're completely soluble. So this produces the fluoride ion. Okay? Potassium doesn't do anything. It's a spectator. We can get potassium in solution without the hydrogens. Okay? If we do that, then what's it going to do? Well, let me check something first before I steal my own thunder. Let me see. All right. Consider this reaction before I move on to the other one. If this is a weak acid, that means it has a reasonably strong attraction for its hydrogen. It does not want to give up that hydrogen. Doesn't want to transfer it. Right? So the ones that it does transfer to this water and make that conjugate acid, we make the conjugate base. Well, if this one has a strong attraction for hydrogen, it doesn't want to give it up. What about this one? It has a strong attraction for free hydrogens, and it wants to go back to that one. So a weak acid produces a strong conjugate base. It wants protons. This one doesn't want to give them up, but once it does, it produces a species that has a strong attraction for protons from any source. And if we put this in aqueous solution, the source of protons is water. So we set up an equilibrium here. We transfer a proton. Now this becomes the acid, and this is the base. We transfer a proton to that HF. And what's left? Hydroxyls. Okay? Now, we can write an equilibrium expression for this one also. We leave the water out because it's a pure liquid. And what we get is a Kb. Right? There's the base. What does it do? It accepts protons. So we put the products in the numerator. It produces some of this. It produces some of that. And it has some of this left. There we go. So that would be a Kb expression for a real reaction, not just this hypothetical one that's there on the slide. All right. So what is, in chemical terms, what is a salt? All right. Let's see. We don't need that right now. In order to produce a salt, we need an acid reacting with a base. And in those terms, I'm talking about an Arrhenius acid base is the best example. So if we have let's say HBr in aqueous solution. And we add to that acid solution a basic solution produced from potassium hydroxide. Okay, so what's going to happen? Well, we studied types of reactions, and this is actually going to be a double replacement. So this hydrogen replaces that potassium, right? And that potassium goes back over here. So we have this cation, this anion together in aqueous solution. And a proton plus a hydroxyl equals what? Water. So whenever you have an acid reacting with a base, it produces a salt and water. Okay? That's a typical acid-base reaction. So a salt is not necessarily sodium chloride. In this case, it's potassium bromide. But the salt is the product, one of the products of an acid-base reaction. That's our chemical definition of a salt. Now, this is, if we evaporated all the water, we'd get a solid potassium bromide, right? There's a definition for a salt. And what I just illustrated here was called a neutralization reaction. When we combine a strong acid, HBr, and a strong base, KOH, we get a completely neutral solution in which there are no excess hydrogens and no excess hydroxyls. Right? We can't claim it's an acidic solution or a basic solution. It is neutral. These are some other examples. There you go. Everything fits the definitions we proposed. Now, in this reaction, you'll notice that both hydrogens were transferred in the reaction. Even though the second hydrogen on that sulfate is weak, the potassium hydroxide is such a strong base that it will remove that second hydrogen with ease. All right. All right. This just illustrates the on the molecular level, a reaction of a hydronium and a hydroxide yields water. In fact, the net reaction here in the solution, this is hydrogen ions, bromide ions. This is potassium ions and hydroxyl ions. And this one has potassium and bromide in solution. These are all aqueous. They're actually separate. We wrote them together for convenience, but in solution, they're all separated. This is still separated. This is still separated. And water. Okay. If we put that reaction like this, like that, notice that you've got some terms are the same on both sides. Remember, we're considering those spectators. We've got bromine here and bromine there. Right? We've got potassium here and potassium there. So what do we have left? what we have left is hydrogen ions plus hydroxyl ions yields water. That is the net ionic equation for all acid-base reactions. In this example here on the slide, instead of using hydrogen ion, they used a hydronium, which is actually what happens in solution. But if you do that, then when this proton transfers to that hydroxyl, we make water, but we also have a water left behind. So now we have two waters. And now it matches what you see on the slide. All right. In a neutralization reaction, what products are formed? Water and salt. Pure and simple. All right. Now we're going to go back to this amphoteric nature of water, where water molecules can react with each other. This is a process called self-ionization. Okay, when they do that, the equilibrium is way, way to the left. They only do it in a small amount. So in that respect, we could say this acid is a weak acid. This base is a weak base. And you have a conjugate acid here and a conjugate base. Okay? So there's another illustration of what's going on. We're transferring a proton from one water molecule to the other and producing a hydronium and a hydroxide. Okay? We can write an equilibrium expression for this. But remember, this is a pure liquid, and these are in aqueous solution. So what's the rule? For equilibrium constants, for the calculations, you don't include pure liquids or solids. So this expression, this K value, we give it a special subscript called W because it's only for water. The Kw is the concentration of hydroniums times the concentration of hydroxyls, right? In the numerator is the products. The denominator doesn't have anything because these are pure liquids. So when we determine this at 25 degrees Celsius, well, 24 actually, but it's pretty close at 25. We get a value of 10 to the minus 14. Okay? One other thing that I left out of the equilibrium discussion, besides the fact that we don't include pure liquids and we don't include solids, we don't include units of measure either. The reason we don't include units of measure is for all the equilibrium expressions that are possible for that thousands of reactions that we could study, the units of measure could be anything because we include the powers. We have a quotient situation, right? So it's too unwieldy to try to keep track of all those units. What we do is we be very meticulous, very careful about our calculations. And if we are, then, and we do a calculation, then we know that the results are going to come out in molarity. Concentrations will be in molarity. Okay. Now, this is something that happens to water always. No matter what you do to it, that reaction is still there. If we dump a carload of hydrochloric acid into a big vat of water, the acid will undergo its reaction, sure, but this one will also be happening. So these reactions happen simultaneously. And anytime you consider an acid reaction or a base reaction in water, or any time a chemical reaction, you always have to remember that this one is happening always. And that equilibrium constant is the same no matter what else we do to it, as long as the temperature is constant. Okay? So, notice with this value, how did we get there? Well, we had one-to-one relationships here, right? So, if we multiply these two together to get that value, what are these concentrations? They have to be equal, because it's one of these to one of these makes one of these to one of those. So the concentration of this one has to be the same as that one. Okay, if this is x squared and this is that value, what is x? What is the concentration here for pure water? Well, take the square root of this. Ten to the minus 7. 14 divided by 2, right? Okay, so each of these concentrations had to be 10 to the minus 7 molar. That condition, where hydrogen ions are equal to hydroxides, or hydroniums are equal to hydroxide, is neutral. It's not acid, it's not base. Now, if we add some acid, right, we tip the balance back toward this one. Let's say we add enough acid to change this concentration. Instead of 10 to the minus 7, 10 to the minus 6, which is a higher concentration, right? When we're talking about negative coefficients, negative powers of 10. 10 to the minus 6. Let's put a table up here. 10 to the minus 6 molar now. Well, if this reaction is happening all the time, and that was 10 to the minus 6, if we put 10 to the minus 6 in here and solve for that unknown, what would we get? Well, 10 to the minus 6 plus 6 and 14 is 8. So 10 to the minus 8 would be the concentration of hydroxyls. And that would be an acidic solution, because the hydrogen ions, or hydroniums, are greater than the hydroxyls. That would be an acidic solution. If we went the other way, say we made this one 10 to the minus 6, then this one would have to be 10 to the minus 8. And that means the hydroxyls are higher concentration than the hydroniums. That would be a basic solution. That's what this chart is trying to show you. All right. So that's the essential definition of acid solution, basic solution, and neutral solution. Okay. So let's try an example here. See if we can use this information. I'll leave that up there for now. All right. Calculate the hydronium ion concentration and the hydroxyl ion concentration as required for each of the following solutions at 24 degrees, and state whether the solution is neutral, acidic, or basic. Okay, so A is what solution? 1 times 10 to the minus 4th hydroxyls. 1 times 10 to the minus 4th molar hydroxyl. Okay? So we want to know both this concentration, which is already given to us, but we also want to know the hydronium ion concentration. So if we take this expression, Kw equals 1 times 10 to the minus 14 is equal to, and I'm going to start substituting hydrogen ions for hydroniums. For calculation purposes, they're equal. They're exactly the same. In chemical terms, of course, the hydrogen ions don't exist separately, but for calculation purposes, they're exactly the same calculation. Right? So now, if we substitute that value in here, we'll be solving for this unknown, correct? So if we solve for this unknown, that means this one must be divided by this one. Okay? All right? So 1 divided into 1 is 1, and 10 to the minus 4 divided into 10 to the minus 14 is the same as 10 to the minus 14 times 10 to the 4th. So you subtract, you add your exponents together. Minus 14 plus 4 is minus 10. 1 times 10 to the minus 10 molar. So the hydronium ion concentration is 1 times 10 to the minus 10 molar. Okay? There's the calculation. And that makes it basic, right? Because the hydroxide ion concentration is greater than the hydrogen ion concentration. That makes it basic. It's also, this one is much less than the neutral concentration of hydrogen ions. Right? That would be 10 to the minus 7. This is much smaller. 3 orders of magnitude. That's 1,000 times smaller. So this one is very basic. Okay, how about B? 2 molar hydrogen ions. Okay, so what's the concentration there? Well, we got the molarity of the hydrogen ions. How about over here? This is going to be now hydroxyls, and this value is divided into that value, 2.0. Okay, so what's that? Well, 1 divided by 2 is a half, times 10 to the minus 14. Or if we modify it to scientific notation, this will be 5 times 10 to the minus 15. 5 times 10 to the minus 15 hydroxyls. All right, it didn't even do a calculation, did it? Well, it didn't do a calculation because this is so much bigger than that. It has to be acidic. There's no other option. Okay. So an aqueous solution in which the concentration of hydroniums is higher than the hydroxyls is an acidic solution. Now, new concept. I've never met a person yet, an adult that is, who hasn't heard of pH. I mean, they throw pH around like they know what it means, right? We're going to define pH, right, in its original form, proposed by Sorensen, another Danish chemist, at the beginning of the 20th century. So think back. We had Arrhenius proposed a definition for acids and bases in the latter part 1880s, and then now we got this Danish chemist who's proposing pH based upon that reaction producing hydrogen ions in 1909, and then in 1923 Bronsted and Lowry came along and proposed an alternate definition for acids and bases. So that's the chronological sequence here. All right, so Sorensen you know what? Earlier I said that Arrhenius was working with proteins. That's wrong. Arrhenius wasn't the protein chemist. Sorensen was the protein chemist. Arrhenius was a physical chemist. Okay, so that aside, Sorensen was working with these proteins, but he was kind of sick and tired of expressing the acidity or the basicity of his solutions in terms of scientific notation, right? Those are big numbers and they get confusing. They take up a lot of paper, right? He wanted a simpler system. And he proposed what he called pH, right? Little p, big H. The big H, of course, stands for hydrogen. And the P, I'm not sure what it stood for. It might be Danish. Or it could be his middle name, Peter. Who knows? But whenever we do the calculation and express the value for pH, it's always little p, big H. If you write big P, big H, or big P, little h, or little p, little h, all three of those are wrong, no matter what the number is. Just a word of warning. Okay, so what he proposed was, with these big numbers, expressing the hydronium ion concentration in terms of, let's use neutral, right? 1 times 10 to the minus 7 molar hydrogen ion concentration. He decided to take the logarithm of it, right? The common logarithm, which is base 10, right? Base 10. So when you transform a number by taking the log of it, what does that mean? The log of this number is the power of 10 that gives you that number. That's the definition of logs. So the power of 10 that gives you that number is what? Minus 7. Okay? He didn't like minuses either. So he put a minus out here. And now, including that one, makes it a plus. So now we have a simpler numerical system to express acidity and basicity in terms of the logarithm of the hydrogen ion concentration. A word about significant figures. If the molar concentration has two significant figures in it, like this one right here, then the pH is expressed with 2 decimal places. So this would be 7.00, right? And if you work backwards, 2 decimal places means 2 significant figures in your molar concentration. So that's how we go backwards and forwards. And that's nothing special to chemistry. That's just logarithms. That's how they work. All right, so what's the pH of this first solution? All right, let's do this. All right, and substitute in that value. 1 times 10 to the minus 4. All right, 10 to the power of minus 4 times a minus is 4. pH. Okay? There we go. How about hydroxyl? Well, that's a little trickier because we can't do the calculation until we get hydrogen ions. So we got to go back to this one. Kw equals 1 times 10 to the minus 14 equals hydrogen ions times hydroxyl ions. And we know what this one is, 0.040 molar. So we divide this one into that one, and we get hydrogen ions. Concentration. So let's see. Where's my calculator? We got 1 exponent 14, change the sign, and divide by 0.04. So I get 2.5 times 10 to the minus 13. So that would go in here. All right, I just take the log of that and change the sign. 12 point, two significant figures, 60 pH. Okay? There you go. All right, what's next? The pH of a solution is 5.85. Okay? What's the hydrogen ion concentration for that solution? Well, what's the definition? This is equal to the negative log of that. So we need to work backwards. We need to solve for this one. How do we do that? Well, first of all, we got to get that negative back over here. You can't resolve a negative log term. So put the negative back over here. That's equal to the log of hydrogen ions. There we go. Now, go to the definition of logarithms. If this is base 10, that means this is the power of 10 that equals that value. So this value is equal to 10 to the minus 5.85. Right? So you need to find that key on your calculator, 10 to the x power. It's usually how it's listed. And it'll be located close to the log key. Right? This is also called the anti-log. The anti-log of, the anti-log of minus 5.85. It's the same thing. So let's punch in 5.85, change the sign, and then find the 10 to the x key. Here it is on my calculator. And I get 1 point, let's see, 2 decimal places, 2 significant figures, and rounding on my calculator, I get 1.4 times 10 to the minus 6 molar. All right. There we go. All right. So we're able now to go forwards and backwards in our calculations. And remember, Sorensen's proposed pH definition is purely mathematical. Whatever concentration you have for that hydrogen ion, you can do a calculation. And sometimes it comes out 0, sometimes it comes out negative, depending on how high the values are. Okay, so what does that mean to neutrality versus acid base? Well, if this is neutral, that's a neutral hydrogen ion concentration. Then the pH is 7. Okay? Acidic solutions will be higher in concentration, right? What happens to the pH? That becomes 6. See the trend? The more acidic the solution, the lower the pH value. So the basic side will be just the opposite. 10 to the minus 8 would give you a pH of 8. Minus 9 will give you 9, and so forth. So we have a scale now of pH. As it gets smaller, more acidic. As it gets bigger, more basic. Here's some examples, natural examples of pHs that have been determined. Egg whites are between 7.6 and 8. There's butter, peas, carrots, tomatoes, all those. I would have liked to have seen what's the pH of your blood plasma. If you've had anatomy and physiology, you probably remember this. When you studied blood as a tissue in, well, actually, wouldn't be a tissue because it's not a single cell type. So blood technically would be an organ. Anyway, what's the pH of blood plasma? It's 7.35 to 7.45. So it's slightly basic, and it's very closely regulated in that range. If it goes below this, you're said to be in a condition of acidosis. And if it goes bigger than this, higher than this, you're said to be in a status of position or a condition of alkalosis. All right. Correct mathematical expression for pH is that one. Or H plus. It works also. All right. So this calculation of pH is a mathematical expression. We can do the same thing for other types of concentrations, right? If we have OH concentration, we can take the negative log of that, right? That's just math. So what are we going to call it? Well, if we use Sorensen's terminology, it would be POH. Okay? Or, actually, we can do this one. Remember the acid ionization constant? We can do that one too. Log, negative log of that equals pKa. Or we could do the one for water, right? Negative log of that one. That's equal to pKw. Right? We know what this one is because we have a value for that, right? 10 to the minus 14. So this one would be 14. Okay? Let's see. I think I've got an animation here. Yeah, there it is. What they've also done here is taken the expression for Kw equals this concentration times this concentration. And we've taken the negative log of that entire equation. Right? So this one would be pKw equals. So what are these? Well, if we take the negative log of that, negative log of hydrogen ions times hydroxyl ions. If you remember logarithms, if you take the log of A times B, that's the same thing as the log of A plus the log of B, correct? Right? That's a logarithmic rule. So that means this one would be negative log of hydrogen ions plus a negative log of hydroxyl ions, right? This is pH, and this is POH equals to pKW. And we determined pKW is equal to 14. Okay? So that makes calculations easier, right? If this is always happening in water, if we calculate the pOH from some value that we're given, we can put it in this equation and find out what pH is without having to go through the trouble of calculating the actual concentration of hydrogen ions. What's the pKa for HF, given that the Ka for this acid is 6.8 times 10 to the minus 4? All right. Just take the negative log of the value, and you get 3.17. So what does that mean? Let's see. Have I got a slide on that coming up? I don't want to steal my own thunder again. All right. As the K gets bigger, right? As the K gets bigger, say instead of what was that? 10 to the minus 4. What if it was 10 to the minus 3 for a K value? The negative log of that. That would be 3, right? So as the number gets bigger, the pKa gets smaller. So stronger acids have a smaller pKa, right? Stronger acids mean smaller pKa. Just like a small pH is acidic, more acidic, a smaller pKa means a stronger acid, which means the solution should be, for the same concentrations of two different acids, the one with the smaller pK will be the more acidic. So this pK is 3.17. All right, so we did the pK on that one already. Why are they 6.3 times 10 to the minus 4? Oh, okay, 6.8. So if we do the calculations for 6.3 times 10 to the minus 4, we should get something close to it, and it would be acidic, right? 3.2 is probably the answer. Yeah. Okay. All right. We're still good on time. We don't want to rush this stuff because these are new concepts, brand new. All right, so if you have a salt, by the chemical definition, and it's a solid, and you put it in aqueous solution, what happens to it? Well, the simple answer is it breaks up into its individual ions, cations and anions. But it also undergoes a reaction with water called hydrolysis. So when it does that, it can produce either hydronium ions or hydroxide ions, depending on which part of the salt is reacting with the water. Now, this is a possibility. It doesn't guarantee that it will happen. For instance, when we get chloride ions from this source, produces chloride ions. If we take this chloride, independent of the acid, We take the chloride as a salt of, say, potassium and put it in solution. Right? This was a strong acid, right? That makes this a very, very weak base. This is a weak conjugate base. Okay, so now put that in solution. KCl goes into solution and produces these ions. So the question is, if it's such a weak base, what is it going to do when it encounters water? Virtually nothing. It's so weak, it doesn't want a proton, right? It doesn't act as a proton acceptor, right? So when this goes into solution, you get virtually no reaction with the water molecules from the chloride ion. But if you do it for this one, HF is a weak acid. This is a strong conjugate base. So it will react with water. And what does it do? It takes a proton from it, leaves behind hydroxyls. There you go. Okay. Now, let's think of when we dissolve a salt in solution. Are we going to get a neutral solution, an acidic solution, or a basic solution? And it depends on this concept of strong versus weak. Conjugate bases. So let's take a look at that. If you get a strong base and a strong acid reacting together, you will get a neutral solution with a salt. If you take the salt and put it in solution and it dissociates, what is it going to do? Since it comes from a strong source, the sodium and the chloride in this case, since they come from a strong source, they're both weak, so they don't react with water, either one of them. Which means that the water stays neutral, right? So if the source of your salt is strong acid, strong base reaction, then you can expect a neutral solution when the salt is dissolved independently into the water. Okay? What if you have a strong acid source and a weak base source? Right? What's the weak base? Well, the weak base is ammonium hydroxide. And the strong acid source is hydrochloric acid. So when it produces water plus the salt, when you put this salt in solution, what do you get? Well, you get ammonium ions and you get chloride ions. So what are they going to do when they go into solution? Right? You get this one and you get this one. Is this going to react with water? No. This reacts with water because it comes from a weak base. This ion reacts with water. And it transfers the proton to water and produces that. Now, which side of this reaction is preferred? Well, this is considered the weak base because it's proton acceptor. This is the conjugate acid. So if this is the weak base, the conjugate acid is a stronger acid. So it wants to transfer that proton to water and makes that. So you get an acidic solution. Now that's the chemistry. The rule of thumb that will help you solve these problems is consider the source. Strong acid, weak base. the solution is going to be acidic. Right? That doesn't tell you the chemistry, but it helps you answer the question. And similarly, if you have the salt formed from a weak acid and a strong base, the solution will be basic. In this case, we have, let's see, sodium acetate. So sodium acetate. Right? Goes into solution, produces sodium ions. Are they going to react with anything? No. It won't react with water at all because it comes from a strong base, right? Sodium hydroxide goes into solution completely. It doesn't want to react with water at all. But if the source here is a weak acid, that's from a weak acid, which makes it a strong base. This is the strong conjugate base of acetic acid. So when you get this part of the molecule over here, it will react with water. It's a strong base, and it accepts a proton from water, and now you get C2H3O2 plus hydroxyls. That makes a basic solution. So if the salt is formed from a strong base and weak acid interaction, then when you put them in solution, you get a basic solution. Now, what happens if you get a weak acid and a weak base together? Well, then it depends on which is a competition between the cation and the anion from the salt. All right, which one? The base will accept a proton from water. The acid will donate a proton to water. So then you have to decide which one wins, right? And we're this course, you haven't got enough background to go into that one, right? It's enough to say that when a weak acid and a weak base form the salt, then it could be either acid or basic. It could go either way. Okay, some salts hydrolyze when placed in water. That is, they react with water to produce hydronium and hydroxide, or both. When the salts of a strong acid and a strong base are placed in water, the result is a neutral solution. All right, now let's talk about buffers. I sort of glossed over the topic of buffers when we were talking about the pH of blood plasma. It's buffered between the pHs of 7.35 and 7.45, right? How does your body do that? Well, it uses a complex buffering system is what it does. And now we need to understand what buffer means. In chemical terms, a buffer is an aqueous solution that when acid or base is introduced to the solution, the pH does not change very much. It changes only slightly. It's not fixed. I mean, it's not rock solid, but it does move only slightly when you add acid or base. Unlike pure water. Pure water, if you add a strong acid to pure water, it will go acidic like that. It's not buffered. But if you add hydrochloric acid to a properly buffered solution, the pH will only change a little bit. It'll go down just a hair. So we need to understand how the buffering system works. It will also, if you add a strong base like sodium hydroxide to that same buffering system, it will also maintain its pH very close to the set point. It'll go up just a little bit, but not much. So what you need in a buffering system is two species. If you add an acid, you need something in that buffering system that will consume the protons that you added, so that they won't increase the proton concentration and thus change the pH. You also need a part of that system that will react with added hydroxyls, added base, such that the pH will also not change with that addition. Okay. So typically, the construction of a buffered system includes a weak acid, a certain amount of weak acid, a concentration, and a certain amount of concentration of the strong conjugate base that results from that weak acid. Right? So if we had, let's say acetic acid. And I'm going to simplify this reaction. I'm going to leave the water out. Right? Let's just say it goes like this, like that, produces that, and the acetate ion. Right? Recognize this is not the chemistry that happens, but for calculations, ease of calculation, we left the water out. Right? It still works. So this is our weak acid. And this is the strong conjugate base. All right. So if we construct our buffer so that we have some of this and some of that in solution, and how would we get it in there at the proper concentrations? Well, you have two ways. You could put acid in there and it starts off acid, and then you could add base to it until you generate some of this, until you get a balance there, and that would be your buffer. Or you could take a salt of this and some acid and put them together in the proper concentration and instantly produce a buffer. So you have to have some of this, and you have to have some of that. So we have an equilibrium set up here with this system. Now, what happens if we add acid? If we add acid, and this is a strong base, this is going to scarf up, to use a chemical term, scarf up those extra hydrogen ions because it's a strong base. And in terms of equilibrium, if we add something on this side, the system is going to respond to consume it. It's going to move back that direction until the equilibrium is reestablished. That's called Le Chatelier's principle. I think we have a slide on that later, so I'm not going to go into it right now. Well, no, we don't. But since next week's lab is Le Chatelier's principle, I better tell you about it. Le Chatelier's principle, it references a system in equilibrium. So if we have a system in chemical equilibrium and we do anything to disturb it, the system will respond in such a way as to minimize the disturbance. So if we add something this side, it's going to shift back that way. If we add something this side, it's going to go this way. If we remove some of this, it's going to go this way, trying to reestablish equilibrium. Okay, so back to the acid-base buffer thing. If we add this, if we add extra hydrogen ions, now it's going to be consumed by some of these and shift this way until we get equilibrium. So we're not going to use all of them up. The added hydrogen, we'll use most of them up, and there'll still be some left over. That's why the pH will shift slightly. So what happens if we add base? Say if we add hydroxyls. Well, the hydroxyls are going to react with the hydrogen ions and produce water. So what does that do? It removes hydrogen ions. Now the equilibrium shifts back to the right and produces some more of these to replace the ones that we lost. And the pH will not change very much. It will change a little, but not much. And the reason it does that is because of this equilibrium setup with a weak acid and its strong conjugate base. So that's what happens when you add acid. Let's see. What two active species are contained in a buffer? Well, a substance that resists change in pH when a small amount of base is added. That's a definition. B is the flip side of that in terms of adding acid. A is base, B is acid, and C is the reason they do that. A weak acid and a strong conjugate base together will establish a buffer. Now there's an ideal concentration for this one and that one together that we haven't talked about yet, and I hope we'll get to that in just a second. Yes, we are. We're going to get to that with the Henderson-Hasselbalch equation. I'm going to leave that there for now. Okay. So Henderson did the first work with acid equilibrium. And he knew that the Ka could be expressed in these terms right there on the board. Right? Ka equals hydrogen ions plus the conjugate base of the weak acid and divided by the concentration of the weak acid. Okay? Henderson was working just prior to Sorensen's work. Henderson didn't know about pH calculations. He only knew about hydrogen ions. And he said, since we know this, we can solve this equation for hydrogen ions. Right? All we need to do is rearrange it. So we've got this Ka, excuse me. Yeah. We've got this yeah. If we keep this one on one side, then this one comes over here times Ka. And then A minus on the bottom, like that. Okay? I just kept this one here and took this term right here and flipped it over here, right next to this one, right here. Okay? That's the work of Henderson. That's what Henderson did. I think the next, there, that's Henderson's calculation. Hasselbalch came along several years later after Sorensen proposed pH. And Hasselbalch took this equation and took the negative log of everything in the equation, like we did before. So if we take the negative log of each side, right, negative log of the whole thing, what does that give you? Well, the negative log of this one is pH, right? pH. The negative log of this one is pKa. And the negative log of these, we want to keep those as is. All right, so we're just going to say negative log of this term divided by this term. Okay? But he didn't like negatives in his equation. Right? Notice that this one times that one is the same as log of this one plus the log of that one. So that's why this one is a negative sign here. But if we get rid of that negative sign, what does that do to this? Well, remember, the negative log of A over B is the same as the positive log of B over A. That's another logarithm rule. So if we can make this one positive now, as long as we switch places. Put the conjugate base on top and the acid on the bottom. pKa equals pH. Okay, so that was Hasselbalch's contribution to this equation. Okay, there we go, and there we go. Okay, that's why it gets both their names, because Henderson worked on it a while, and then Hasselbalch took that work and went next step. This is the equation that we use today, the Henderson-Hasselbalch equation. Okay, so what we notice is that for the acid that has this particular dissociation constant here, the pH of the solution will be the same as long as this ratio is exactly the same. So the ratio of the conjugate base to the unionized acid, if that ratio is the same, then the pH of the solution will always be the same. So you could have very high concentrations here or very low concentrations here. And the ratio would be the same, which means the pH would be the same for any of those solutions. It's all dependent upon the ratio of the conjugate base to its acid. So what's the pH of a buffer solution that is 0.45 molar acetic acid and 0.85 molar sodium acetate? All right. Let's leave this here. Let's leave this right here, because 0.45 molar acetic acid, 0.45 molar acetic acid, and sodium acetate delivers the same molarity of the acetate ion, right? When it goes into solution, the sodium is a spectator. The acetate now is 0.85 molar. Okay, so we have the concentration of this one and the concentration of this one. What's the pKa? Well, the Ka is 1.8 times 10 to the minus 5. So the pKa of acetic acid is a negative log of 1.8 times 10 to the minus 5 molar, right? Which is equal to, let's just do the calculation, 1.8 exponent negative 5, and take the negative log of it. Let's see, two significant figures. 4.74 would be the pKa. Okay, so now we can find out the pH if we put in 4.74 here plus the log of the ratio of the conjugate base to the acid concentration. Okay, so let's say 0.85 and 0.45. Did I get those right? Yeah. 0.85 divided by 0.45 is 1.89. And then we'll take the log of that, which is 0.276, and we add that to 4.74, and we get 5.02. Okay. Oh, I animated it. That's good. 5.02. That's the pH of our solution. And we made it by not titrating it, not doing an acid-base titration, but simply by adding the components wholesale. Right? We put this much acid in here, and we put this much conjugate base in here as sodium acetate. And that delivers a buffer with a pH of 5.02. Okay. The mathematical expression is A and B. Yeah, base over acid. As long as you understand that the base is the conjugate base of the acid, a weak acid and its conjugate base. Okay. One other thing that I don't think I have a slide on, but it's important. So when we actually do titrate a weak acid with a strong base, we get what's called a titration curve. Let me get another marker. That was going out on me. That was not much better. Let's try one in my pocket. Here we go. So we can mark pH on this scale, and we can mark added sodium hydroxide on this scale. Okay? So when we start off with, say, acetic acid, a weak acid, the pH is going to be down here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, about pH 3 right in here is where we start. Actually, it's closer to 4. No, 3 is right. 3 is right. Okay, so it's going to go up in the beginning because it's only acid and we're neutralizing the acid. So it goes up and then it levels off. And it stays there for a while. And then it goes like that, and then it levels off again. So that's a titration curve for a weak acid. And what we find is, what region of that curve does the pH not change very much? Right in here. There, there. This is the buffer zone. Right? So how do we know the ratio of conjugate base to the acid? Well, we know that this point right here is neutralization. That's when the moles of base is exactly equal to the moles of acid. Right? We've neutralized it right here. And that occurs at some pH. 3, 4, 5, 6, 7, 8. It's actually up here somewhere. Okay, so this means that the amount of conjugate base now is everything. We've converted all of this to all of that. That means this is the total A minus. The total concentration of A minus is here. So what's in here? Well, you notice that about halfway, about 1/2 neutralization is right in the middle of the buffer zone. So that means we need half of this value. Okay? So what does that mean? That means that the best buffer position is where you have a ratio here of 1 to 1, exactly equal of these values. If these are exactly equal, then you have 1 divided by 1, which is what? 1. And what's the log of 1? Well, the power of 10 that's equal to 1 is 10 to the 0 power. So that makes this whole term equal to 0. And the best pH for the buffer is equal to the pK. So this value here, over here, this pH is equal to the pKa. So if you have a weak acid, a monoprotic acid, and you've determined that its pKa is some value, that is the same as the pH for the best buffer position. Exactly equal acid and base. All right. Okay. So let's move on to the next topic. Let's see, what are we going to talk about? Electrolytes. All right. All right. What's an electrolyte? Well, an electrolyte is operationally defined. In other words, we say what it is. An electrolyte is any substance, when dissolved in water, will allow the solution to conduct electricity. That's why it's called electrolyte. So if you have a solution here of some salt, sodium chloride, any salt, then if you put two electrodes in it here, positive electrode, negative electrode, and attach them to a battery, I think that's right. Maybe it's the other way around. Anyway, and a light bulb, like that. If this is an electrolyte in here, you will get a light. It conducts electricity. Okay? Non-electrolytes, however, will not conduct electricity. They may go into solution, yeah. For instance, table sugar, sucrose. It will go into solution as much and as fast as you want to put it in there, but it will not conduct electricity. And by the way, pure water is an electrical insulator. Pure water does not conduct electricity. Why? Because there are not enough ions to move the charge. Right? You only have a few hydrogen ions and a few hydroxyl ions, not enough. So water is an insulator. If you put something in it that makes ions, like sodium chloride, like sodium ions and chloride ions, now it will conduct electricity because you have a mobile ion. If you have sodium chloride salt, solid, like that, that is an insulator. If you put an electrode on one side of a salt cube and an electrode on the other side of the salt cube, it will not conduct electricity because the ions are not mobile. You either have to put it in solution or melt it. There's a strong electrolyte. You get a very bright light bulb. By contrast, a weak electrolyte will only light up a little bit. So a strong electrolyte would be something like sodium chloride or hydrochloric acid, strong acid, but a weak acid like acetic acid, vinegar, will only conduct electricity slightly. Right? So there's a correlation there. Weak electrolytes, as far as acids go, weak acids make weak electrolytes, strong acids make strong electrolytes. And soluble salts are all strong. Okay. Now here's a concept called equivalence. Let me see here. Yeah. This is the next to the last topic. What do we mean by an equivalent? Oh. An equivalent of any ion is the amount of that ion needed to supply 1 mole of positive or negative charge. So now instead of focusing on the ion itself as a whole, we're focusing on the charge. So 1 mole of sulfate ion is actually 2 equivalents of sulfate ion. That is, it produces 2 negative charges for every 1 mole of the polyatomic ion, whereas chloride is 1 equivalent of chloride is 1 mole of chloride. 1 mole of phosphate ion is 3 equivalents of phosphate ion. Now, why would we want to do that? Because so many of the reactions in chemistry are based upon ion balance, right? And the calculations become easier if you know the equivalence of your ion rather than its molar amount. If you only know the molar amount, then you have to go back to the equation, the operating equation, to determine the molar ratios of the reactants and products, just like we've done in the past with stoichiometry. Now, 1 milli equivalent is a milli, right? What's a milli? A milli is 10 to the minus 3. Right? Remember your prefixes that we learned in the first chapters? Milli is 10 to the minus 3, or 1,000th of. So 1 milli equivalent is 1/1,000th of an equivalent. All right. When you go to the doctor and give them a blood sample, or you go to the let's see, what's the name of that company? LabCorp. If you go to LabCorp and they take blood and they analyze it, very often one of the things that your doctor wants to know is what's the balance of your electrolytes. And these are electrolytes because they could conduct electricity if we used electrodes. Sodium, potassium, calcium, magnesium are common positive electrolytes in your blood. Chloride, bicarbonate, some proteins produce negative ions. Hydrogen phosphate, sulfate ions are some of the common ones. And they were reported not as molar concentration, but as equivalent concentration. So they're reported on the basis of the number of ions per liter, right? So sodium ions, 138. Well, since sodium is 1 plus and potassium is 1 plus, then there you can see the relationship there, right? The sodium is 138, say 5, it's about 25 times more concentrated sodium than potassium in this sample. Calcium, on the other hand, is 4 milliequivalents. Right? So its molar concentration would be half of that. Right? It would only be 2 molar. And magnesium would be 1.5 molar. Okay, it's just another way of reporting the values. So let's say we've got a problem here with concentration of calcium ions present in a sample is 5.3 milliequivalents per liter. How many milligrams of calcium ion are present in 180 milliliters of sample? All right, what we've got here is a dimensional analysis problem, unit conversion, pure and simple. So since it's worked out there, I shouldn't have to do it. We're starting off with 180 milliliters of sample. Okay, so we want to convert that to liters. Right there. So we can use 5.3 milliequivalents to find out exactly how many milliequivalents there are in the sample. Right? Then we want to convert milliequivalents to equivalents, and then equivalents to moles, because 1 mole of calcium produces 2 equivalents. We need to cancel the equivalents. Right? And that means 2 equivalents per mole. So now we've calculated the moles of calcium ions. Now we can calculate the mass. So this is the molar mass, produces how many grams, but the answer wants what? Milligrams. So we have to convert grams to milligrams. And that's how many milligrams of calcium ions are present in that sample. It's purely dimensional analysis. Let's see. I've gone over time, but there's nobody here for the lab, so I'm going to continue with a lecture and finish it up. While discussing mixtures of ions, a chemist focuses on ion identity and amount rather than the compounds that supply the ions. The concentration of ions is specified using what unit? Well, the equivalent unit, of course. That's what the equivalent unit is for. We can talk about the total amount of ions without reference to what the ions are, because now we're focused on their charges. Acid-base titration. We talked about this a little earlier. This is the net equation for an acid-base titration. The acid part is right here, the base part is right there, and it always produces water. So what do we mean by a titration? Well, a titration can take many forms. Let me put it that way. But in terms of acid-base titration, we have an unknown concentration of a substance in the Erlenmeyer flask there on the bottom, right here. Okay? We don't know what the concentration is, but we have measured out the volume. We know the volume accurately. Now, what we have in this device called a burette, which is able to deliver very small droplets of a base, in this case. Let's say there's an acid in the Erlenmeyer flask and a base of known concentration in the burette. If we know how much we added, we can calculate the moles of base that was required to neutralize the acid. And the calculation then will give us the concentration that is in the acid. Right? Now, why does that work? Let me see if I've got it here. Acid-base titration. Okay. You need some more explanation. Okay. If we know the concentration of base, and we know how much of it we use, what does that tell us? Remember, molarity equals moles per unit volume. So if we want to know moles, we had molarity times volume. So molarity times volume equals a certain value, moles of base. Now, this works as long as the acid produces one proton and the base has one hydroxyl. It's a one-to-one relationship. If we have the molarity of the acid times the volume of the acid in that little Erlenmeyer flask, then that's equal to the moles of acid. Well, as long as these two are equivalent, they're monoprotic and monohydroxyl, then you could say the moles of base equals the moles of acid. And that means this expression is equal to that expression. So if we know the molarity of the base, we know how much was delivered to neutralize the acid, and we know the original volume of the acid, then we can calculate the molarity of the acid. Now, if you've got a diprotic acid or a dihydroxyl or a triprotic acid, then you have to have the balanced equation, or you have to learn how to use normality, and that talks about equivalents per liter rather than moles per liter. But that's too much to cover for this class, so we're going to skip that and just say for monoprotic acid, monohydroxyl bases, this works. That's a titration. What we're looking for is the equivalence point, right? So if we have, for example, if we're titrating acetic acid with sodium hydroxide, that's going to yield water plus sodium acetate. C2H2O2. Okay. So what we want is the equivalence point. That point at which all of the sodium hydroxide and all of the acid are consumed. And this is all you have left. None of that is left. That's the equivalence point. And it occurs at a different pH for different weak acids. Right? This one occurs in the neighborhood of like 8.3. So you can either do that titration that I showed you earlier with the sigmoid curve, or you can use a pH indicator, one that changes color in very close to the pH at which this reaction is complete. Right? And one that's typically used for this reaction is called phenolphthalein. Right? It changes color between 8 and 10. So it's a good choice. And that is not the equivalence point indicator, but it is the end point. All right, so here we get change of color, and that tells us when the reaction is complete. Okay. For titration of sulfuric acid with sodium hydroxide, how many moles of sodium hydroxide will be required to react with 1 liter of 0.5 molar sulfuric acid to reach the endpoint? All right. Remember what we said. When you combine a strong base and a strong acid, the salt that results dissolved in water is neutral. So the pH at which these two react and reach their equivalence point is 7. Okay. So we can approach it 2 different ways. We can approach it using the balanced equation. I need another marker. We can use the balanced equation, H2SO4 plus sodium hydroxide yields sodium sulfate plus water. And if we know the concentration of, let's see, moles of sodium hydroxide would be required to react with 1 liter of 0.5 molar sulfuric acid. 1 liter of 0.5 molar sulfuric acid. We want to know how many moles here. Right? So remember, volume times molarity is moles. So 0.5 times 1 is 0.5 moles. That's moles of sulfuric acid. But this one takes 2. Right? That's the balanced equation. So the ratio here is this many moles of sulfuric acid. We use our stoichiometry, right? H2SO4 and sodium hydroxide. What's the ratio? 2 here, 1 there. So it takes 1 mole of sodium hydroxide. All right. All right. The other approach is to use the net equation. All right. How many hydrogen ions, how many moles of hydrogen ions are here? This is moles of sulfuric acid. How many moles of hydrogen ions? Well, you got 2 for every one of these. So that means you have 1 mole of hydrogen ions. 1 mole of hydrogen ions. So 1 mole of hydrogen ions needs 1 mole of hydroxyls. Well, 1 mole of hydroxyls in this molecule is 1 mole of sodium hydroxide because it's only 1 for each sodium hydroxide. So that's another way to approach it. Right. That was the stoichiometric way right there. Well, actually, no. That's how many moles of hydrogen ions, and then you need exactly the same number of hydroxides. All right. When determining the concentration of an acid or base, a blank is performed, a titration, an acid-base titration, using an indicator to visualize the desired pH. Okay? That takes care of that one. So a solution containing hydronium ion, concentration of 9.34 times 10 to the minus 4th molar, has a pH of negative log of what? 9.34 times 10 to the minus 8. Molar hydrogen ion concentration. So let's plug it in and find out what it is. 9.34 exponent negative 8. Take the log and change the sign. Let's see. 3 significant figures. Whoa. 7.030. pH. Okay. So it could be any one of those. Except that this is slightly basic. Very slightly basic. So it's either B or D. It also has a hydroxide ion concentration of what? Remember this one? Plus POH equals 14. So 14 minus 7.03. 7.03 minus is 6.97. POH is 6.97. And now we can find out the hydroxide concentration by taking the anti-log of the negative. 10 to the minus 7 equals what? So let me change the sign and then take the anti-log. Is 1.07 times 10 to the minus 7. Okay. So it would be D. It's slightly basic with a concentration. It says it's neutral. Okay. The claim is that it's so close to 7, we're calling it neutral. But technically, it's slightly basic, right? 7.03. All right. So let me see how close we are. This is the last slide in the set. All right. 25 milliliters of acid requires 14.8 milliliters of a 0.351 molar base to completely neutralize it. What's the molarity of the acid and what 2 products are formed after neutralization? All right, in this case, we have to assume that we're dealing with a monoprotic situation. So the acid would be monoprotic. What's the molarity of the acid? So we have molarity of the acid times volume of the acid equals molarity of the base times volume of the base. Right. So what is it asking? Molarity of the acid. So we need to solve this for molarity of the acid. like that. So the molarity of the acid is equal to 0.351, 0.351 molar times 14.8 milliliters divided by the volume of the acid, 25 milliliters. Now notice that I didn't change the volume to liters, right? Milliliters, milliliters. Why? Because milliliters cancel, right? They're the same units. So since this is a ratio, you can use milliliters in this expression. So what does the calculation give us? Well, let's see what it is. 0.351, 14.8 times that, and 25 divided into it. So I get 25. Let's keep three significant figures just for giggles. 0.208. 0.208 molar is acid molarity. And what two products are formed after neutralization? Always a salt and water. There you go. Right, we have to assume that the acid is monoprotic and the base is monobasic or monohydroxyl. Otherwise, it doesn't work. Okay, that's it. That's it for chapter 10. Now we've gotten both chapter 9 and chapter 10 covered in lecture. Next week, we're going to come back and review for exam 4. That'll be on the 28th of April. And the following week is finals week. So on May 5th, or you can show up in class if you want to, that's fine. If not, I'll be here. So if you show up in class, I'll give you a paper exam. If you take it in Brightspace, then you need to get finished on Friday. So I'll have enough time to check all the grades and be ready to give them to the registrar by the deadline.